from a mentor, a Siemens business. He's a functional safety professional. And the title of his talk is Rethinking Your Approach to Safety Analysis. Dirk obtained a Master in Microelectronics Engineering from the Technical University of Berlin and is functional safety professional mentor. Hello, Dirk. Can you hear us?
I can hear you loud and clear. Do you understand me?
Okay, thank you, Dirk. Go ahead.
Okay. So I assume you're able to understand me? Because now there is the line is again dead, so I'm not sure if I can be understood by the rest of the audience.
I can understand you, Dirk. This is Sergio.
Okay. Hi, Sergio. So then I'll just start. In case there is any problem, don't hesitate to interrupt me either directly via audio or via the chat. Thanks for the introduction. And thank you for giving me the opportunity to talk here today. My topic for today's talk is a presentation about a new approach to run safety analysis. So, is everybody able to see my screen? I take this for the yes. So the agenda which I set up for today's talk covers a very brief introduction because the guys who talked earlier already covered most of it. So, and then I will go into details concerning safety analysis. We already heard about this today during the earlier talks. What is functional safety? So we generally separate this into two areas: avoidance of systematic faults and mitigation of the so-called random faults. These two areas are covered by the ISO 26262, and this is a topic for today's talk. I won't cover system faults, means does my system operate safely, which would touch environmental issues and car to environment stuff. And also I would not touch today some malicious faults, means if some guys or girls with bad habits would try to attack a car. This is not part of today's call. I'll solely focus on the most left two columns, means systematic faults and random faults. So, again, with two pillars on the left side, I think most of us know what these things are all about concerning avoidance of systematic faults, means we write specifications, we do some functional design, we do some functional verification, and so on. However, topic of my talk today is the right side of the fail safety. Means if we want to get a design safe, then additional steps need to be taken into consideration. This means the planning, safety analysis, safety insertion, safety verification, and at the end of the day, we need to ensure that everything is compliant to what the standard requests from us. So today's topic is the safety analysis. Basically, goal of any safety analysis step is to get an overview about basic metrics, and also check if the design which we intend to set up is appropriate concerning architecture, and the architecture needs to meet power and targets. This can become a problem because as soon as we realize that after insertion of our safety mechanisms, the area targets cannot met anymore, there's a significant problem within the overall design cycle. However, there is some more stuff on stakes because we need to come up with the metrics for our certification authorities, and we need to check that what our experts have estimated can be proven. So, first step to reach these goals is what we call base failure rate calculation, and therefore Mentor has it available, which we announced recently. It's called SafetyScope. So what SafetyScope basically does, it calculates base fit rates, and I'll cover those in a second with certain input parameters. However, the output of the tool may be of more interest for the audience, because as listed over here in this area of the presentation, this is the output of SafetyScope. Base failure rate metrics, you see lambda permanent, lambda for transient faults. Then discounted means whenever, say, diagnostic coverage comes into place. However, as being visible, this design currently doesn't have any safety mechanism in place. The diagnostic coverage is 0. And on top of this, SafetyScope, an output, also tells you where inside your design are the biggest contributors. Means you get an output file which contains the instance name according hierarchy, and then the contribution concerning permanent and transient fault. Of course, the top level has 100%, and then there's a sum up of the various instances. So you can see as a basic step for the analysis, take the output of a first run and investigate which parts of your design contribute the most to your overall fit rate. Now the question may come up, how does the tool calculate these values? And there is this basic equation. It's defined in the standard for fit rate calculation in the IEC 62380 standard. And this is simply or basically what the tool is doing. As inputs, we have a lambda for the package and lambda for the die. Any question? I hear some noise in the background. I take this as a no. Then I go ahead. Okay, so for the calculation of the package, we need information about the technology of the package material, the package specification, and of course also information about the environment and inside which the design needs to work with. And then as a next step, there is also information necessary about the used technology. Again, application and used technology with respect to semiconductors being used. All of these values are taken into consideration for calculating the lambda of the so-called of the die itself. Means we cover the package, we cover the die, and now there's one thing missing. And this is the overall number of transistors. And this is where SafetyScope comes in place and provides the necessary calculations for the users. How does the tool do this operation? Basically, it starts from so-called Startpoints, which are state element outputs and primary inputs, and the according endpoints, means the inputs for state elements and primary outputs. So as being colored over here, there we have Startpoints, there we have endpoints. And the cones is everything in between. And this is in a very simple overview how the tool starts calculating stuff. So we have a start point, we have an according endpoint. So the tool calculates transistors of the endpoint and the transistors of the cones. And this basic calculation will be ran through the whole design. To be able to get to these informations, the entry point for the tool itself is RTL code, VHDL, Verilog, system Verilog. And then SafetyScope runs a very basic internal synthesis to get to a netlist to be able to run these calculations, because therefore a gate level representation is necessary. And then, as already outlined, we have all the necessary parts of the formula being filled up with values, and then the tool can come up with according calculations for the basic fit rate. However, SafetyScope provides one more step, which I will outline now in a second. One key metric for functional safety is the so-called diagnostic coverage. I'm assuming everybody in the audience knows what this is about. The ratio of the failures detected or controlled by a safety mechanism to the total failures in the element. And this is where SafetyScope can also provide value. As already been outlined, we already run a base fit rate calculation, means we generated values for permanent and transient lambda for recording submodules, depending, of course, on the used technology. And now we can go one step further. For example, here in this block, we already have a safety mechanism with a diagnostic coverage of 99% for both permanent and transient errors. And so you can see, and this is something SafetyScope will calculate according to the input of this ACC block over here, that the overall diagnostic coverage is 45%. So as already outlined in the earlier talk, for example, for ASIL-C, I think we need 95 or something. It's clearly visible that this won't be sufficient. And this is where the next step of SafetyScope comes into play, the so-called safety exploration. You can define safety mechanisms with their according diagnostic coverage and can adjust those to your according design hierarchies and instances. And then the calculation can be done again, and then you can check, do you meet your safety goals or not? And this is a key aspect, so you can run what we call analysis, means as being visible over here, you have, for example, parity, you have duplication, triplication, ECC, or logic bit with the according impact on the diagnostic coverage. However, also with the impact concerning resource utilization. And so you can run an investigation. What would happen if you add parity? What would happen if you add triplication? How does your overall diagnostic coverage change? And does this finally fit into your safety goals? And so this is for a very basic example what would happen. So if you run the analysis, and by the way, I did not mention, but of course this is an information of importance. This analysis is done on the gate level netlist within SafetyScope. So what you do from a user's point of view, you run a configuration file which contains the parts to which you want to attach safety mechanisms, and then you simply apply the proposed safety mechanisms to your design hierarchy. And then the tool starts calculating again how this manipulation would have an impact onto the diagnostic coverage. And so I try to outline this here in the picture. For example, if I add a lockstep mechanism to my cache controller, then how would this have an impact onto the diagnostic coverage? If I do packet CRC, how would this have an impact onto the diagnostic coverage? And so I can just, by changing this configuration file, applying additional mechanisms or removing mechanisms up to my considerations and estimations, I can directly see the impact, what would happen if I added these kind of safety mechanisms to my design. And then, of course, this will also have an impact on to my fit rates. And then I can, at the end of the day, I jumped ahead, I can run this exploration. As you can see, these are the safety mechanisms we added into the configuration files, their according impact, and this is what would happen in the netlist. I have an endpoint, start point, and there I add parity, and then the necessary comparator checks as safety mechanism if any fault became detected or not. However, for this dedicated application, the cone in between would not be checked. As you can see over here, we check from there, we check and also from there. However, everything in between won't be checked. Therefore, a dedicated end-to-end analysis would be required, which the tool also supports. And so, by running this additional step, I can run a safety exploration, means I can check what kind of impact instantiation of dedicated safety mechanisms would have on my design. And this is where we see the value of the tool overall. On top, this is the regular flow. You have your requirements, you do your design, then you run safety insertion, you run your verification, and you run your fault campaign, and then you check if your safety goals were met. If not, then you need to go in various iterations. However, by applying SafetyScope, you apply SafetyScope over here, and then you can save all these explorations, because just by applying SafetyScope, you already get a direct information if your safety goals can be met or not. And then you only need to run the analysis and iteration steps within the tool, which is quite simple, instead of running it over here, which may have an impact onto the overall design, concerning area and all the other things. So, today I only talked about safety analysis. However, all of these things only make sense if this is a complete flow. And I did not cover the parts now in the blue sections, because next step in the flow would be what we call design for safety. Means the safety analysis as an output, safety exploration, and the safety insertion tools take the output from the analysis tool and insert the safety mechanisms into the real design. So over here, this is all done on the gate level netlist. However, the real insertion takes place within this step, and then real safety mechanisms are mapped automatically into the design according to the output of the analysis. And then, as the ISO requires safety verification, this safety analysis tool also generates a fault list. According to the results of the safety exploration, the fault list becomes generated, and the fault list acts as input for the safety verification, means for the fault simulator. So that at the end of the day, you run a safety verification based on your safe design, means the design which includes the safety mechanisms, and then finally you get your validated metrics for final diagnostic coverage calculation. And when this loop is closed, then you can provide the metrics for diagnostic coverage, latent point failures, single point failures, and basic overall fit rate into your FMEDA to close the loop and to provide the necessary values to conclude the analysis step. This is what we as from Mentor call Mentor Safe IC, because this is the complete flow which we can provide with our tool suite. So, conclusion. We started talking about elimination of systematic faults. Therefore, we have according tools in place for requirements management. We have according tools in place for verification and design for test. All the tools which I talked about today have undergone tool qualification by TÜV. And we have an according consulting team in place which has the necessary expertise to work on site with our customers. To tolerate random faults, we run safety analysis. I talked about this in detail. And then also I touched briefly the design for safety and the safety verification tools. Means we are in a situation now to provide a complete flow as well as for systematic faults as well as for handling random faults. And this concludes my presentation for today. I am open and available for all kinds of questions.
Hi. Thanks, Dirk, and thanks for stepping in a little bit earlier than expected. We have one question online, which I'll read out. How similar is this flow when used for non-automotive safety standards?
You are very difficult to understand. I could only get some brackets. Okay. The entry was how safe is, and then the rest of the sentence was missing on my side.
Let me repeat it. How similar is this flow when used for non-automotive safety.
The question which I got is how similar is this flow for non-automotive applications? Is this a correct summary?
Yes.
There is no difference because the tools themselves are not depending on any flow. Means if you want to run, for example, for Milero or for industrial applications, you can use same flow because at the end of the day, you need to provide similar outputs. And so the tools are not depending on any flow or any standards definition.
Okay, any questions?
Das